Hello, ladies and gentlemen, and welcome back to Algebra 2 Distance Learning with Mr. Hagedorn. Today, our lesson 8.5, Find Probabilities of Independent and Dependent Events. Obviously, by the names themselves, independent means they're completely separate from one another. Dependent always has some dependence on the previous event. We'll talk about that as B given A, but we'll talk about that here in a little bit. We're going to start out with the probability of independent events. Now, the probability of independent events is probability of A and B, which is a little different than the OR we dealt with in 8.4. And to find that, we simply take the probability of A times the probability of B. So if we take a look at our first example, it says in a survey at Miller Park, 50 of 75 male fans and 40 of 50 female fans said that they favor the Brewers team mascot, Hank the dog. So if one male and one female are randomly selected, what's the probability they both favor the new mascot? So this one we start out with the probability of A being the males. So in this case, the probability of A would be 50 over 75, which I would simplify down to 2/3. We don't need common denominators because we're going to be multiplying, not adding. Then the probability of B I would take as the female fans, which would be 40 over 50, and simplifying that down would give us 4/5. So the probability of both of those occurring, meaning the probability of A and B, would be their product. So in this case, that would be 2/3 times 4/5, or the probability of this event would be 8 over 15. And you will notice today that the overall probability that these occur are going to be generally less than the original amounts because we're taking the fraction of a fraction, or as you see in the next case, the decimal of a decimal. So the next example says a survey found that 46% of parents surveyed say they read to their kids at least once a week. So if 3 parents are selected at random, what's the probability all 3 will say they read to their children? Well, in this case, the probability of success is 46%, or as a decimal, 0.46. So even though there's 3 events here versus the 2 we saw in the first one, they're all still independent because they have no overlap or they have no correlation with the other parents. So in this case, the probability of A, B, and C occurring would be equal to the following: 0.46 times 0.46 times 0.46. And if you multiply those together, that's approximately equal to 0.0973. So since the original problem started with percentages, I would just say we'd round this one here, and you can round it really any way you want, but I'm just going to simply say it's about 9.7% for that probability. So there are some examples of dealing with independent events. Now, dependent events are a little bit different. 2 events, A and B, are dependent events if the occurrence of one affects the occurrence of the other. In other words, is there some correlation between them? Is there some overlap that's occurred? The probability that B will occur given A has occurred is called the conditional probability of B given A, and is written as the probability of B, that upright, that pipe, A. And I'll just talk about it as B given A. So the probability of A and B in dependent events would be the probability of A times the probability of B given A. So here we have a couple of different scenarios that I'd like to go through with you, and they deal with our 52 card standard deck. So in this case, what's the probability of drawing a spade, replacing that, and then drawing a club, and then drawing a spade, not replacing it, and drawing a club? So if we take a look at this one, the first event, A, with replacement means we choose it, we put it back in, and we randomly choose another card. So remember, in our deck, there are 4 suits and there are 13 cards per suit. So the probability of drawing a spade, so the probability of a spade would be equal to 1/4. 1 out of every 4 cards in a deck is a spade. We put that back in, and then we draw out a club. And again, that would also be 1/4. The reason, there's no overlap. There's no correlation. We put the card back in and we drew from the original 52 again. So in this case, the probability of drawing a spade and a club would be equal to 1/16. Now if we take a look at it, but now we take a look at it from the standpoint of if we don't replace it. So there's no replacement. So once again, the probability of drawing a spade would be equal to 1/4. Still, 1 out of every 4 cards in that deck is a spade. But now, since we took that out, now we've got to take a look at what did we do to change that. So now, what's the probability of drawing a club given that we drew that first spade? Now there are still the same exact amount of clubs in that deck because the first one was a spade. So there are 13 clubs. But now we're taking that 13 out of 51 cards. So in this case, the probability of S drawing a spade and drawing a club would be 13 over 204. And if you do a little quick math there, the probability of the second event is actually a little bit higher than the first event because in this one, we took out a failure. So it makes it more likely to happen than the first event. Now, if we go back up and take a look at the second scenario, here we're going to draw a jack, then draw another jack. So with this one, the first one was, again, with replacement. So there are 4 jacks out of 52 cards in that deck. So the probability that the first one that we draw, the probability of 1 jack, would be 1 out of 13. So we put that card back in. The probability of drawing the second jack would also be 1 out of 13. So the probability of 1 and then 2 jacks would be equal to 1 out of 169. So very similar to the first event because the 52 goes back to normal for both. Now the second part of this scenario involves doing it without replacement. So we take it out, we leave it out, and then we draw again. So the probability of drawing 1 jack would still be equal to 1 out of 13, because 1 out of every 13 cards is a jack. However, if we take one of the jacks out of the deck and leave it out, there's only 3 left in there out of the 52 cards that we have. So 2 given 1 would now be equal to 3 out of 51, or 1/17. So now if we multiply those two probabilities together, then the probability of 1 jack and then a second jack would be equal to 1 over 221. Now in this scenario, the second event is less likely to occur because in this case we took out one of our successes versus the first one where we took out one of our failures. So it's an interesting situation that we have, and you always need to pay attention to those details. All right. Last example I'd like to go through with you here today, ladies and gentlemen, is one dealing with a study about wearing seatbelts and the percentages of people that wear them. So it says a study reports that 69% of adults wear seatbelts while driving. A high school student also wears a seatbelt 66% of the time when the adult wears a seatbelt and 26% of the time when the adult does not wear a seatbelt. What's the probability that a high school student in the study wears a seatbelt? So for this, I'd like to do a little tree diagram to kind of show you the differences that we have between adults wearing and students wearing. Okay? So the first part of this would be, let's start with adults wearing seatbelts. Okay? If the adult wears, in this case, it says 69% of the time. So I'm going to write that as a decimal, 0.69. If the adult wears the seatbelt, then the percent of the students wearing seatbelts, let's call them SW, is 66%, which means that the other students not wearing, would be what's left over, which would be 34%. Now the next one, the other part of this scenario, is what happens when adults don't wear them. So I'm just going to call this adult not wearing. That would be 31% of that group. If 69% wear them, that means 31% don't. So now if we take a look back up at what we were given, it says only 26% of the students wear them when the adults don't. 0.26 for that. So students not, or what's left over, would be 0.74. So now what we're looking for is the probability that a high school student wears a seatbelt. So for this, that would give us the following two scenarios. In the first one, if the adult wears it, 0.69%, we're going to take that times 0.66 because it's adult wearing and student wearing. So that's one scenario. Or, going back to 8.4, we add together the other scenario as well. Adult not wearing and student wearing, we'd also have to multiply those together. So that would be 0.31 times 0.26. So if we do the math on this, in the first scenario, the first one that we had there where students and adults wear them, that would give us about 0.4554 plus our second scenario of adult not but students still wearing it would be 0.0806, which would give us a grand total of 0.536. Or, to answer our question, what's the probability? The probability would be about 53.6%. So that one kind of brings into play a little bit of 8.4 and 8.5 from our lessons in this unit. All right, ladies and gentlemen, so we've taken a look at a couple of different scenarios now, with 8.4 being the OR scenarios of overlapping and disjoint events, and then today the AND scenarios of independent and dependent events, both of which are probabilities that we're going to take a look at in our practice worksheets. Please make sure that if you do have any questions, come to class time and ask them, and if there's anything else I can do to help you, please make sure you let me know by sending me an email. Again, ladies and gentlemen, as always, stay safe and stay healthy, and Lord's blessings on your day.